In this chapter, we're going to be discussing reactions that occur in aqueous solution, and in particular, the reactivity of ionic compounds. In a general sense, if we have some reaction that is shown here between some reactants, which are represented by capital A and capital B, they will then produce two hypothetical products, compounds C and D. In this case, there are stoichiometric coefficients, which are the whole number multiplication factors in front of each of the reactants and products. The general process involves, for a solution, some volume of a solution that has some molarity. We can use that molarity, in the case of compound A, to then determine the number of moles of compound A in the solution. We can then use some molar ratio between the species A and some other species, say the other reactant compound B, and this ratio is based upon these stoichiometric coefficients in the balanced reaction. And then finally, we can use the molarity of the solution that contains B to determine the volume of B necessary to react with A. As an example of this type of reaction, we have a question that states, what volume of a 0.250 molar H2SO4 solution is needed to react with 50 milliliters of a 0.100 molar sodium hydroxide solution? You see here the balanced chemical reaction in which one sulfuric acid reacts with two sodium hydroxides to produce sodium sulfate and two waters. In this particular case, again, the process will involve figuring out from the volume of the sodium hydroxide solution given in the question how many moles of the sodium hydroxide are present in this solution. We will use the molarity to do that. And then the next step, we need to know a stoichiometric relationship between the sodium hydroxide and the sulfuric acid. This comes from the balanced reaction. And then finally, by knowing the molarity of the sulfuric acid solution, we can figure out the volume of the sulfuric acid. So, if we start with our 50 milliliters of the sodium hydroxide, and we use a conversion into the liters, so essentially moving the decimal point 3 places to the left, we can come up with the volume of the sodium hydroxide in liters, and then the volume of the sulfuric acid that we need would be, take the 0.0500 liters of sodium hydroxide, use the molarity to cancel the liters, and then the mole ratio between the sodium hydroxide and the sulfuric acid, which is 2:1 from the balanced reaction. That cancels the moles of sodium hydroxide. And then finally use the molarity of the sulfuric acid to cancel the moles of sulfuric acid. And this will give us the liters of the sulfuric acid. So that turns out to be 0.0100 liters, which then we convert back into milliliters, and the final answer with 3 significant digits is 10.0 milliliters of the sulfuric acid solution. There are 3 general types of reactions that we are going to discuss when we're dealing with aqueous solutions. The first type is a precipitation type of reaction. This is when you mix 2 solutions of a soluble ionic compound, and the one or possibly more of the products happens to be insoluble in aqueous solution, therefore forming a solid, which quite often is a very finely divided solid which forms a cloudy solution and is referred to as the precipitate. The second type of reaction involves reacting an acid with a base to do a neutralization reaction. whenever one reacts an acid with a base, the products are always going to be water plus the salt or ionic compound that would come from the cation and anion of the acid and base that you started with. So, and then the third type of reaction involves the transfer of electrons from one reactant to another. This is referred to as oxidation reduction reactions, or also known as redox reactions. One of the concepts that we will need to understand when we deal with solutes that are dissolved in aqueous solution is the idea of being an electrolyte. If we have a molecular compound where there are polar or covalent or possibly covalent bonds involved, the compound is typically not going to break apart into ions and therefore would remain intact as a molecule, and this is referred to as a non-electrolyte. In some cases, the compounds may break apart to some very small extent, producing ions, and in that type of situation, they might be a very weak electrolyte. But in general, molecular compounds are non-electrolytes. They do not conduct electricity. In contrast to non-electrolytes or molecular compounds, ionic compounds, when they dissolve in solution, will break apart into their component ions, cations and anions, and these cations and anions get surrounded by water molecules and therefore become quite mobile, and they are able to conduct electricity. So, any ionic compound dissolved in water produces what we refer to as an electrolyte solution. So, an example of this is something like sodium chloride, table salt. When that dissolves in water, it produces sodium ions and chloride ions that are well separated from one another and quite mobile, and as a result, this would conduct electricity quite readily. So, these are an example of a physical reaction in which we can reverse this by removing the solvent, and we go back to having the solid sodium chloride. This slide helps us visually understand what happens when solid sodium chloride dissolves in aqueous solution. So on the left here we have a regular repeating pattern for the lattice of sodium ions, which are the small white colored balls, and the chloride ions, which are the larger green. And so if you place a piece of solid sodium chloride in water, the water molecules will collide with the ions that are on the surface, and since water is a polar molecule, the positive ends of the water molecules will interact with the negative ions, the chloride ions, whereas the negative ends of the water molecules will interact more strongly with the positive ions, the sodium ions. And occasionally these molecules have enough kinetic energy to break off the ion from the solid, and this then draws the ions into the solution where they become surrounded by the water molecules, as you see here on the right.